Hello, so today I'm going to be talking about mathematical methods in the Renaissance, specifically navigation and geography. So I'm going to start off with just a little bit of background, what the motives were for exploration at the time, and then we'll get into some of the influence and some of the cartography, which is map making. So we'll talk about some of the important people who helped develop maps at the time and what their mathematical methods were for that. And then I'm going to talk about some of the mathematical instruments that they used during navigation at the time. So let's jump right into it. So a little bit of background, the motives for exploration, they sought new trade routes, specifically with their trading partners in the East, which was India, China, and Japan. They wanted an alternative route to the Silk Road, something that was a little bit faster because the Silk Road was on land. So they wanted a quicker sea route. And there was a lot of pressure at the time on spice trade. So having that alternative faster route would prove to be very beneficial. Additionally, the Catholic Church restrictions on diet and meat consumption resulted in the search for new fishing grounds. And so this is actually believed to be the reason for exploration in North America. And then there was also the rise of monarchies in Europe. So there was more centralized authority and more wealth. And so with that extra wealth, monarchies were able to fund exploration. An example of this would be with Christopher Columbus. So he was funded by King Ferdinand and Queen Isabella of Spain. And so with the rise of monarchies and the extensive wealth, they were able to do more explorations. Additionally, there was vast improvements were being made to the navigational skills and technology. And so I'm actually going to talk about a little bit of those navigational technologies later on in this presentation. And then just overall interest in learning new ideas along with foreign culture and goods. So I'm going to talk a little bit about the influence. Because little exploration had been done before this time, we remember this from history class. Early maps assumed that the world was flat. And so as exploration expanded and we were able to discover new land, the misrepresentation of the curvature of the Earth became pretty apparent to mathematicians who recognized the necessity of translating the points of a sphere onto a plane. So that's just translating our world onto a map, a paper map that's flat. And so Ptolemy was also a huge influence during this time. His Almagest and Geography served as a huge inspiration to mathematicians during the Renaissance. And his books actually depicted a spherical world on a plane chart. So he was very important to map making at this time. So cartography, which is map making. We have a couple important people who developed maps throughout this time. We have Pedro Nunez, who talked about the rhumb line or the loxodrome. And the rhumb corresponds to a course of fixed direction. And so he found that the angles between the rhumb and the latitude lines were fixed. And since direction was defined relative to the lines of longitude, the angles between the rhumb and each successive line of longitude were fixed as well. And he correctly found that on the surface of a sphere like the Earth, the loxodrome represented a spiral approaching a pole, which we can see in this figure here. We see this spiral is approaching a pole. And then we can also see those angles right there between the lines, and they are fixed. One of the goals of cartography, however, was to depict the loxodrome as a straight line on a plane chart so that a ship's course could be plotted using a ruler. And Nunez was unsuccessful in doing this. So we have Gerardus Mercator, and he was able to represent the rhumb as a straight line in 1569. Sorry. He developed a grid of lines of longitude and latitude. And geometrically, he postulated that because the rhumb line was to be straight and the angles with the lines of longitude were to be fixed, then the lines of longitude had to be parallel. And so on the globe, we know that these same lines of longitude converge at the poles. And so while making his map, Mercator stretched the lines of longitude so that they would be proportional to the secant of the latitude. And this actually resulted in distortion. So I'm going to talk about that a little bit. In this picture, it's kind of hard to read. It's a little blurry. Also, it's written out, so I don't know if this is like the original copy that was made. But on this side, we can see this is on the Earth. And so on the Earth, the lines of latitude remained evenly spaced while the lines of longitude converged. Yet on Mercator's projection, the lines of longitude were equidistant and the lines of latitude diverged. So we can kind of see the difference between the scales on Earth compared to Mercator's projection. And so this actually caused a problem, and we'll see this in my next slide. So talking a little bit about Mercator's distortion on a specific example. So his maps distort the shape and size, relative size of continents. So for example, on Mercator's map, Greenland appears to be similar in size to South America, when in fact South America is about 10 times larger than Greenland. So we could see in this picture on the left, this is Mercator's representation, and the purple is Greenland, the pink is South America. And you can see that it's very, very similar in size, and that should not be the case. On the right side is the actual size of Greenland compared to South America. You can see it's actually much smaller. So Mercator was very off in this way. And I just thought this was something very interesting to talk about, especially since Mercator's projection is the system for which most other maps were constructed. Mercator's projection was corrected by Edward Wright in 1599. So we're going to talk a little bit about Edward Wright. So him and Thomas Harriot analyzed the nautical triangle that Mercator's projection yielded. And so the vector given by the ship's speed and direction was considered to be the hypotenuse of a right triangle on the plane chart. And the legs of this triangle were consisted of the changes in the latitude and the longitude for some unit of time. So again, this picture is kind of hard to see, but this right here, this horizontal line is the change in longitude, and the vertical line is the change in latitude. And these are the legs. And then we have this point right here. This is the ship's current position. And then the hypotenuse is the ship's movement. And so they also use spherical trigonometry with respect to navigation and map making. So we have Tycho Brahe and Richard Norwood, and they postulated that we can use spherical geometry if we're given the distance between any 2 points whose latitude and longitude were known. We could use that to determine the displacement between any other known coordinates. And these applications from Mercator's projection are very important for navigation. Unfortunately, though, those that were closely involved with navigation, so sailors, they had little understanding of these concepts, or they refused to accept them. So many navigators regarded even the idea of a mathematical projection of the perfectly spherical Earth onto a plane chart as black magic. And at the same time, navigators claimed that the convergence of the lines of longitude at the poles was ridiculous and imaginary, especially since no one had physically ever experienced that phenomenon. And so they maintained their faith in the proven old maps. So they refused to use the newer, more mathematically advanced maps, which proved to be a challenge. So these new paradigms were created to kind of help navigators understand navigation a little bit more in this mathematical respect. So we have Martin Cortez, and in 1551, he used the width of 37 degrees latitude as a basis for spacing the lines of longitude. And then we have Petrus Plancius, and in 1592, he designed the world map on a simple cylindrical projection. And so this is less abstract than Mercator's projection, so it was a little bit easier for navigators to understand. And then we have Richard Norwood. So we already talked about him a couple slides back, but he's here again because he realized that The segment of a great circle represented the shortest distance between two locations on a globe. And so we actually kind of talked about this a little bit in class. Dr. Ryan kind of showed us a picture that if we have a segment of a great circle, we can use that to find the shortest distance between two locations on a globe. And Norwood's method involved plotting segments on the great circle on a Mercator chart and approximating it by a succession of short rhumb lines. So this technique was incorporated. This technique incorporated several of the key innovations of Renaissance mathematics and cartography. So it incorporated the rhumb line, Mercator's projection, and the nautical triangle. So overall, during this time period, mathematicians responded to the needs with an advanced form of cartography. And so now I'm just going to talk a little bit about the mathematical navigation instruments, because these are also scientific instruments. So we have dead reckoning. So rather than using the latitude and longitude system, because like I stated before, navigators weren't fully aware or didn't fully understand what that was yet, navigators substituted latitude with a Roth theta system. So they began with a known position, and the navigator would measure the heading. So the heading is the direction that the front of the ship is facing. They would also measure the speed of the ship, the speed of the ocean currents, the downward drift of the ship, and the time spent on each heading. And so just think about that. It's kind of interesting to wonder like how they were able to measure each of those things. And so they were able to do this using reliable instruments, which I will talk about a little bit later. But this dead reckoning method helped reveal the course of the ship, the course that the ship had made and the distance that it had covered. And so they were able to do that with the help of some instruments. So next I'm going to talk about instruments for measuring latitude. We have the celestial globe, which is a mounted sphere that depicts the positions of the stars in the sky. And so the celestial globe was a great instrument to use before Mercator's charts, but once Mercator's projections started becoming the preferred way to measure latitude and map routes, the celestial globe kind of fell out of use. And the celestial globe would not have been possible without Ptolemy's celestial spheres, because like I stated before, Ptolemy had a huge influence on the mathematical measuring instruments and the methods used during the Renaissance. And now we have the astrolabe, which measures the angle between the horizon and the North Star. And the North Star was the preferred star for measuring latitude because it is less than 1 degree from the North Celestial Pole. And so the astrolabe is a large brass ring with an alidade, which is a sighting rule. And so to use this, the user held the astrolabe by the loop at the top and turned the alidade so that he could see the stars along its length, and then read the altitude off of the scale engraved on the ring. And so it was difficult to perform this with only one person, because if you can imagine, if you're standing on a moving ship, it's going to be hard to hold the astrolabe, balance that, and then look into it and try to measure everything all by yourself. So typically they would have 2 or 3 people doing this at a time. And so I actually have a little video that kind of shows how they use the astrolabe. So I'm going to go ahead and play that.
The astrolabe was originally an Arabic instrument. It was also used by the Spanish and Portuguese during the Age of Exploration. It was made of brass, heavily weighted so as to give it stability on the deck of a pitching ship. The terrestrial version was a flat plate. The mariner's version was pierced with holes to allow the wind to pass through so as not to affect its reading. Now let me take a sight. I turn towards the sun, allow the sun's rays to pass through the upper hole, line them up on the lower hole, and then read off the scale. Now that seemed easy, but imagine yourself on the deck of a pitching ship. Sometimes the astrolabe was used by 3 mariners, one to hold it, one to turn the movable arm or alidade, and another to read off the scale.
All right, and so that video kind of just helps show you what the astrolabe is, what the alidade was, that middle part right there, and then how to use it.
The astrolabe.
All right, so next we're going to talk about the quadrant. So with the quadrant, the user would measure the altitude of the North Star by looking through the peephole, which is this part on the side. And they would take a reading where the short line intersected the scale on the outer edge of the arc. So just reading that, it makes no sense at all. I have another video that kind of shows how they use that. That short line that they talked about right here in this description, that actually hooks onto here at the top and hangs down. It's not shown in this picture, but it will be shown in the video, so you'll kind of get a sense of how they used that. And it gets its name because it's shaped like a quarter circle, and it was originally proposed by Ptolemy. So again, we see how important he is during this time period. So now I've got a little short video that kind of explains how to use it.
The quadrant is 1/4 of a circle. It's usually made of brass or wood. From the top is hung a plumb bob. Along the lower edge is a scale. Early mariners sighted along the edge to the celestial body, reading off the lower scale the angle that the body was above the horizon.
All right, so in that video and in this picture right here, you can kind of just see that line right there. That's what I was talking about. Whenever you hold it up and you look through the peephole, you can see that the line will hang at a certain point on that scale, and you can measure that. And I'm just going to talk about one more, if this would work. There we go. I'm going to talk about the cross staff. And so this is just another important instrument that navigators would use while they were exploring.
An instrument that wasn't affected by pitching decks and high winds like the quadrant and astrolabe is the crossstaff. It's made of a wooden staff, 3 or 4 wooden transoms or cross pieces. These correspond to approximate angle of the celestial body above the horizon. To use the instrument, I removed 2 of the transoms, bring it up to my eye, and sight towards the sun. I move the transom to block the sun at the upper edge and line the horizon up at the lower edge, and then take a reading.
So that one, even after watching the video, it's a little difficult to understand, but navigators at this time were able to understand it pretty well. And so all of these instruments rely heavily on angle measures and scales and lots of different mathematical concepts. And although mathematicians created these instruments before the Renaissance time period, throughout the entire Renaissance, because exploration was flourishing, mathematicians were constantly improving these instruments. And so it is because of these mathematical methods for measuring latitude and altitude and all of that kind of stuff that navigators were so successful with exploration during this time.
An instrument that
All right, and then just a couple other navigational tools. So they used a magnetic compass, which, and with that, the North Star kind of gave a good approximation of the true north, which is the magnetic pole. And they would also use an hourglass or a sand glass to keep track of time. And then they also used a lead and line. And so they would have a piece of lead attached to this line, and on that line they would have knots at evenly spaced intervals, and they would throw the lead over the ship into the water, and then they would let it fall, and they would keep track of how many knots passed by as it was falling to the bottom. And then once it hit the bottom, however many knots passed by, they would use that to measure the depth of the water. And so that is all I have for today. So there was a lot of mathematical methods used in map making, and a lot of those methods were too advanced for navigators to understand. And so the development of those instruments that you saw throughout this entire presentation helped make navigation a little bit easier for those sailors and those navigators. So yeah, thank you so much for watching.